Okay, guys, to finish off 3.3, I want to look at one more theorem called the conjugate zeros theorem. If f of x defines a polynomial function having only real coefficients, so let's say you have a polynomial and you only have real coefficients, so regular real numbers, there's no i's in there, okay, which is 98% of the time, but there are some cases where you do have i's for your coefficients. You might see one or two in the homework like that, okay? And if z equals a plus bi, so that's a complex number right there, is a zero of f of x where a and b are real numbers, then the conjugate, the complex conjugate of that, a minus bi, is also a zero of f of x, okay? So the idea here behind this is I need this one and I need this paired with it because when I multiply it out, it should give me only real numbers. And we know to cancel any imaginary numbers, we multiply by the complex conjugate, if you recall, way back from 1.3. That's why it's needed. So for example, just a quick example of this is, let's suppose we have f of x equals x squared plus 1, okay? Well, if you do want to factor that, then we would get this, f of x equals x plus I and x minus I, okay? And notice positive I is really just 0 plus I, and minus I is just 0 minus I. So notice these things are complex conjugates, but notice that I need the positive and the negative. Reason being is x squared minus xi plus xi is I know the outer and the inner terms, when I FOIL this out, are going to cancel. So I'll be left with no imaginary parts. So that is why we have to have complex conjugates if in the original function we only have real numbers for coefficients, okay? Then I get minus I squared, and I remember that I squared is just -1, and now I see, oh yeah, that worked out just fine. That was the function. Okay, so they have to come in complex conjugate pairs. So let's try an example out of the book. So this is number 68 in the book on 3.3. And what they want us to do here for 68 is they want us to find a polynomial function f of x of least degree having only real coefficients, okay? So when I see that it has only real coefficients, that should make me think, oh, okay, need to keep track of complex conjugates. And zeros as given, assume multiplicity 1 unless otherwise stated. So 68 gives us 3 plus 2i is a 0, -1, and 2. So here's what I know. The real parts, I know that I have f of x equals x plus 1. That's from the -1, 0 that they gave me. And they also said 2 was a 0, so I know that x minus 2 works. But then they said that one of the zeros was 3 plus 2i. So this is x minus 3 plus 2i, okay? Don't get too bogged down in the algebra. It's not too bad. And now we say, oh, shoot, if I have a complex number as a 0, then I know its conjugate has to be a 0. Well, that means I have to have x minus 3 minus 2i as a factor, right? I just switched the sign. If I do that, I know, as long as I do my math right, that the imaginary numbers will go away, right? Because I just want a polynomial function with real coefficients. Putting in this complex conjugate of this one ensures that, okay? So I'm just going to leave these alone right here for now. And just to make things maybe a little bit easier is I'm going to go ahead and distribute the negative here. So this is x minus 3 minus 2i and x minus 3 plus 2i, okay? So I'm going to start by multiplying these guys together, okay? And then I'll multiply these through later. So f of x is equal to x plus 1, x minus 2, okay? Now, to do trinomials, I have to do x distributed to all three, -3 distributed, -2i distributed. There's going to be 9 terms there, okay? So first one, x times x is going to be x squared. x times negative 3 is minus 3x. X times 2i is plus 2xi. Now negative 3 times x is minus 3x. Negative 3 times negative 3 is plus 9. And negative 3 times 2i is negative 6i. Okay. Now I need to do negative 2i times each one. Negative 2i times x is minus 2xi. Negative 2i times negative 3 is plus 6i. Okay. And negative 2i times positive 2i, that's going to be negative 4i squared. Okay. Whew. Hope I didn't mess anything up. Here's the thing to notice. We got positive 2xi, we got negative 2xi. We got a negative 6i and a positive 6i. And then I have some stuff I can combine together after there. And I can realize that I squared itself is negative 1. So writing this out, we get f of x equals x plus 1 times x minus 2 times x squared. Combine your x's, so I guess that's going to be minus 6x plus 9 minus 4 times negative 1. That's really just plus 4. So of course I can make that a little simpler. F of x equals x plus 1, x minus 2, then x squared minus 6x plus 13. Whew. Okay. Now, just to show you that this does multiply out and you can expand it out, which is the way I think my math lab wants you to do it, I'm going to actually multiply this out. So this is x squared minus 2x plus x is minus x minus 2 times x squared minus 6x plus 13. Now, if I go through on this one, I have to do this distributed everything, and I'll actually expand it out this time. I just feel like it's a little bit safer. Minus x times that whole second trinomial minus 2 times that whole second trinomial. So let's see what we get. We get x to the 4th minus 6x cubed plus 13x squared minus x cubed plus 6x squared minus 13x minus 2x squared plus 12x minus 26. Okay. And from here, if I combine like terms, I have an x to the 4th. Okay, so I'm good there. In fact, I'll do it in blue. I have a negative 6x cubed, a negative x cubed. I guess that's going to be a minus 7x cubed. I have a 13x squared, a 6x squared, minus 2x squared. That's going to be a positive 17x squared. Okay, so I took care of my squareds. I have a negative 13x plus a 12x is minus a regular x. And then finally, I have the minus 26. So here is your function, fully expanded out, that has all of those zeros. And notice that there's no imaginary stuff here, thanks to using that complex conjugate.